So today I'm going to talk about this Kraft-McMillan theorem, which we used in last talk to prove that Shannon's source coding theorem. Now I just give a recap of this notation first. So let X be a finite set. Yeah, like in last talk, the X has a distribution, but now for present this Kraft-McMillan theorem, we don't care that at the moment, I think. So X is a finite set, and we also take a sigma. Sigma is also a finite set. Then definition. This is a recap from last time. And encoding is a map C, let me call it C, from X to the set of words in sigma. And encoding is an injective map. And we also notice that given such an encoding, we know there exists a map called I call it extension of the map. Denoted by C prime is the map, is the obvious map you can define out of C from the set of words in X to the set of words in sigma. So the idea is you take words in X, the image will be a words in sigma defined by this expression. So that's encoding. Now let's look at a special encoding, which is called uniquely decodable encoding. So an encoding is called uniquely decodable if its extension is injective. So this means that if you have a code words, which is the image of this, an element in the image of C prime, then you can determine its pre-image uniquely. Let's look at one example, which is called prefix code. So a prefix code an encoding C from X to sigma star is a prefix encoding if the following holds. So for all, let me call x1 xn. So for all code words, for all such words where I is not equal to j, CSI is not a prefix of CXJ. So this is saying no code words is a prefix of the other code word. And we're saying this is an example of this uniquely decodable encoding. So why is this? It's because, so to show it is, let me move.
Let me ask a bit of a silly question. So
yeah.
When we say an encoding, I guess we mean it maps X to non-empty words in sigma, right? But that's not stated. But like C prime, well, will have the empty string as part of its output because you can feed in the empty string. And I guess the meaning of prefix with the empty string is also a little unclear. So maybe it's by encoding we mean, I guess we take as a hypothesis that C of X is non-empty, right?
Yes.
Cool.
Yeah. So, right, let's see why this prefix code is uniquely decodable. So if I have a prefix code from X to sigma star, so to show it is uniquely decodable, I want to show this extension is injecting map. So for any element in image, I have a unique pre-image. So if I take elements in the image of this C prime, so I take a code word, I keep using S. We want to show like there is a unique. We want to show that if we have such a code word in the image, we can find this unique. Its pre-image is unique. So by the definition of extension, we know this word is given by this. This is actually this. Now let's look at each of these terms. So if we just write CX1, the image of X1 to be say T1 dot 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 TL1, and I use 1 to index this. We do this for each of these CXI. Say T1 dot 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 TLN N. So we read this code from the beginning. If as we move on, if we stop it here, we observe this part coming from another CXJ, then we know this CXJ will be a prefix for CXY, CX1. So this cannot happen because our code is prefix code. So we can move until here, then we can read X1. But what happens if we move beyond this point? If we move beyond this point, if we can decode this part to be another CXJ again, then this will then CX1 will be a prefix of CXJ. But our code is prefix code, so this cannot happen. So when we read this code, at this stage, we can surely see this coming from X1. And we do the same thing for each of these terms. We know this one is a unique thing sits inside the pre-image of this code word. Yeah, so we can see this prefix code is a uniquely decodable code. Now we are able to state this Kraft-McMillan theorem. So recall we fix this to finite set at the beginning. And let's write there are n elements in X and r elements in sigma. Now consider a function on X. So let L be a function on X valued in positive integer. So because X is finite, this is the same as a tuple. So this is the same as we have a tuple in this set. Now the theorem says that there exists a uniquely decodable encoding C such that each length of this CXI is equal to Li. Li, I mean L applied to Xi, or Lxi, and we denote this by Li. If and only if our this tuple of numbers satisfy this inequality. So this is the theorem, and now we are going to prove it.
Sorry, does it say if and only if the sum of the r's is less than 1?
Oh, can you see it again?
Does that say if and only if on the bottom left there?
Yeah. Yeah.
Thank you.
Yeah, if and only if, yeah. Yeah, I
Awesome.
guess.
Cheers.
Yeah, this. Okay, then. Yeah, this is the statement. Let's look at the proof. Let's do this direction first. So if we have this inequality, we can construct. Let me put it this way. We want to show this direction. If we have this inequality, then we can construct a uniquely decodable code satisfy that property. So the idea is that we construct the code, then show it's uniquely decodable. So this is the direction we want to prove. So suppose we have this. Now let's proceed this proof. So I will write the general argument on the left-hand side, and we will do an example simultaneous on the right-hand side. Yeah, so we can also assume we reorder this tuple, so we can assume L1 is less than L2 less than Ln. In this left-hand side, my example will be r equal to 2 and n equal to, maybe it's not good, just r. So r is the size of sigma equal to 2, and n is the size of x equal to 5. Now assume we assume L1 less than L2 less than Ln. So let's take an example here. Say 2, 3, 3, 3, 3. So the first step is we construct this full R-ary tree. So let A be a full tree of depth Ln. So in this case, we will have a binary tree, full binary tree of depth 3. Now, if we have this full R-ary tree of depth Ln, we notice that every word of length L less than Ln corresponds to a node in this graph, in this tree at depth L.
So the depth is sort of one less than the number of rows, right?
Yes. So this is depth 3.
So I guess the root node is the empty string. Is that how you think about it?
Yes. Yeah. Yes. Now, so yeah, this is this observation. Now let's construct this code, this encoding. We have this tree now. Now for each step 1, for each x, let's do x1 first. So step 1, we take x1. For x1, we define cx1 to be a word corresponding to a be a word corresponding to a node v1 of A at depth L1. So here we know the L1 in this example, the L1 is 2. Then we define Cx1 to be any nodes in depth 2. So any 4. Let me just choose the first one. This is the first step. Now the second, let's move on to the second step. Then I had to...
Yeah, that should be about right. Maybe just walk a little bit further. Yeah, too far. Yeah, you kind of want to come back to around here. Yeah. Yep, that's it.
And I'll keep my picture. Oh. Now the second step is, so we already pick words for x1. The second, oh, so the second step is I remove all descendants of v1. So our picture is here. And we pick v1 to be this one. Now we remove this subgraph. So by doing this, we notice that
What's the problem?
I can't erase it, this green thing here.
Yeah, there's a bit of a bug. Let me try.
Anyway, I will just use black to cover it. Okay, then remove all descendants of v1, descendants of v1. By doing this, we remove r to the power of ln minus l1 leaves of the full array tree, right? Yeah, then we repeat this procedure for x2, xn. So there is a problem that we have to make sure that, because at each step we remove some descendants, which means we remove some leaves, and we have to make sure the number of leaves we remove is smaller than the leaves we have for this full boundary tree. But this is given by our assumption. Note that we have this inequality. Maybe note that we after this procedure, we remove this many leaves. And by our assumption, we know we have this smaller than one times r ln so we have to make sure that we only the number of leaves we remove is smaller than the leaves we have. So in the end, let me back to this example. Say for each x2, I choose this because the tuple I choose is 2, 3, 3, 3, 3. So in the rest of the words, I choose vertex on depth 3. So I will just choose this forward. So in the end, I get a code. In this example, the code is given by, I take x1 goes to v1, which is 0, 0. S2 goes to v2, which is 0, 0, 0, 1, 0, 0, 1, 0. Yeah. And x3 goes to 0, 1, 1, and x4 goes to 1, 0, 0, and x5 goes to 1, 0, 1. And notice in this example, this code is a prefix code, so it's uniquely decodable. This is true in general.
Sorry, how did you get those results? Like the 0, 0, 0, 1, 0?
In this example, right? So if you go in this tree, if you go left, you get 0, and if you go right, you get 1.
Oh, okay.
Yeah.
Awesome. Thank you.
Yeah. So this procedure produces us a. So. Okay. Yeah. So we obtain a prefix code, which is uniquely decodable. C from X to sigma star. And by our construction, we know that Cxi equal to Li for all I equal 1 to n. So this gives us one direction of the theorem. Are we happy with this proof?
Wait, I think I missed the inductive step there somewhere. So that sum is less than or equal to r to the ln. But
yes.
So what? Why put r to the ln there?
Oh yes, this is a number of leaves we have for this full ordinary tree, right?
Right, but don't I also need to know that I can choose one at the right...
The number of leaves is...
at that depth, but don't I also need to know that when I go to the next step, there's enough leaves left, there's enough nodes left at the right depth for me to pick? Did you prove that? I mean, xi, you choose a node at depth li, right?
Yeah. Yes.
I mean, if all the L's are small, couldn't I have run out? Why don't I run out?
Yeah, because we have this assumption. This assumption basically is inequality, right?
Mm-hmm.
So, yeah, we have assumption that sum is less than or equal to 1, and we multiply r to ln on both sides, we get this inequality. And this is the leaves, number of leaves we removed.
Yes.
And this is the total leaves we have.
Yeah. Yeah, okay.
And our assumption guarantees that we have enough leaves. So the number of leaves we remove is always smaller than the number of leaves we have.
Okay, I see. So the reason we order them from L1 up to Ln is that, I mean, you can't do this choosing deeper nodes first because you might later somehow remove its parent. So you have you do those first.
Yes.
And then, okay, and you're saying that yeah, all right, I see. Cool.
I should emphasize the ordering. Make sure that well, after we remove we first deal with the words with lower depth. Then we do this. Then we won't delete the nodes on further depths. So that won't be a problem.
Yeah, it seems quite relevant to.
And in total, the leaves we did.
Yeah, the fact that you can just sum up the number you remove and that is sufficient also hinges on the order of this removal somehow, right? So you can't run out of nodes at depth 2 because if you did, then there's no deeper things somehow, right? Wait, so maybe I'm still not clear on. So I have a bunch of 2s in a row in my list of L's. So suppose L1, L2, and L3 are all 2. So then I've got r to the ln minus 2 plus r to the ln minus 2 plus r to the ln minus 2. And 2 is small, so that's a large power of r. Now, isn't it?
Yeah.
You're saying I can't have run out of those.
If you have 3, 2 there. Yeah, if you have like 3, 2 there, you can see that because they are small, then their inverse, that r to the minus li will be big. Then that bound will tell you. Say in this case, if you have this, let me move to this side here. If you have 2 here, you will see this will be r minus 2 plus r minus 2 plus r minus 2, which will be 3 and 4. Then you can only have, when these things are small, then the number of n has to be small as well. So the remaining thing you can do is, you can only have 1 more 2, otherwise it will break that bound.
Yeah. Okay.
Yeah.
Cool. So that's the end of the proof, right? Well, you did one direction.
That's the one direction.
Yeah. All right, let's move to the second set of boards if you're ready. That's over here.
Yeah.
Okay.
Yeah. So the other direction is if we have a uniquely decodable code, satisfy that condition on the length of each code words, then this inequality holds. So we let C be an encoding.
Okay. Sorry to interrupt, but I think I understand. So this final inequality you wrote is true, but I feel like actually it's a special case of the check that you want to do at each step. I mean, at each step to check there's an available node at that depth, you have to do the same calculation, but it's sort of like the common factor is not r to the ln. So you can count at each stage how many nodes at a given depth are removed, and that's a power of r. And then using the same inequality, you can check that there are always enough available at each step. And this is kind of like at the end also this check is a similar thing. It means that kind of at the final depth there's still anything available. But yeah, okay, I get it. Sorry to interrupt. Please continue.
Yes. Yeah, that's fine. Yeah. So let's say be an encoding such that its extension is injective, and each CXI has the right length. Now let's consider this number P. Now let M be a natural number. Let's consider the power of M. Then we can rewrite this as I1, IM. We just spell out this power. We have this. Now we claim this map. The map from this. By this I mean the integer from 1 to n. This map given by if I take a tuple and map it to this word in T. X, not S. X1 SIM is injective. Yeah, and this can be proved in the following way. Suppose you have these two things are equal. Why? And since this is unique decodable, this extension is injective, implies these two words are equal. And this tells you this. These two are equal. We also note that the length of such a word.
Sorry, what did I miss about this claim? Why is this not obvious? Or is that what you're saying?
Yeah. I was going to ask that.
Yeah, it's obvious, I guess.
Okay, good.
So you're proving that C prime is injective, but isn't it like assumed to be injective? Or am I missing something?
Yeah, it's obvious, this claim. Yeah.
Okay, that's
okay, cool.
Yeah. So we also note that the length of this word will just be the sum of this number. Now by change the way of counting, recall we have this will equal to I1 equal to 1 and IM equal to 1 minus. So each of this power will give us a words in T coming from a words of length M in X. So we change the way of counting. We know this equal to this Q L R minus L. Well, L from 1 to. We know the maximum length of such a word will given by M times L max, where L max is the largest number among this L. And this QL, so L max equal to this, and QL is the number of words in this set. By S to the power of M, I mean all the words of length M in X, not in X. Of length L. Is this step clear?
Yep, I think so.
Yeah.
Yeah, you probably want to stand about where I am now. Yeah, that's good. Mm-hmm.
Now we notice that for each L, there are at most R to the power of L words. So QL will less than R to the power of L. So this number will be bounded by this, which is equal to M L max. Then we take the mth root. So we know p is less than equal to this. And remember, our n is any natural number. And we also know this converge to 1 as m goes to infinity. Then this tells us p has to be less than or equal to 1.
That is
so for each
quite
m,
clever.
Yeah, the proof is not hard, but how they start this, how to get this idea, I have no clue.
Well, it has a bit of a similarity to the last part of the source coding theorem where you talk about blocks, maybe. I'm not sure if that's where the idea for taking the mth power came from. But yeah, that's very neat. So where exactly does the injectivity come in? It's in the part where we...
Yeah, when we...
Right.
Yeah, for this change, this
right.
change of counting, I think.
Yeah.
So each of these index provides you a word uniquely.
That's pretty satisfying. Low tech, but nice.
Yes.
So that's it, right?
Yeah, that's it. There is also a proof which for this direction, but for the special case when they code you have is a prefix code. But I guess this general case is good enough.
Yeah.
Or do you want to say that special case?
Yeah. I think that's a good place to leave the proof. I wondered if it might be useful to, if you don't mind, I'll just translate your example over to the board here and draw it as nested boxes, because that's also a kind of convenient way to think about. So let me redraw your diagram first.
Yep.
First of all, thanks, Zhongtian. That was a great talk. Yeah. Does anybody have questions for Zhongtian? While I'll just draw for a bit and then maybe make a comment, but feel free to ignore me until then.
Thank you. That was really good. I have a dumb question. But why is the absolute value of C prime equal to the sum of the Li1 to Lim on the second last board?
Second last board. This one, right?
This bit here.
Yeah, like because this thing is equal to this, right? By our definition, this extension is given by this. And this will just be concatenation of each of this code word. And each of these will have length Li1. And when you concatenate them, the length will add together. We will add this length together.
Right. It doesn't multiply. Okay.
Yeah. Yeah, like you have AB and you have A, then ABA will have length 2 plus 1, 3.
Yeah. Awesome. Thank you.
No worries.
Any other questions for Zhongtian? Okay, well, if not, I'll try and translate this to... So maybe the very original way to think about the meaning of codings in the sense we've just described in connection with entropy is to go right back to Maxwell's demon, right? Where you're talking about particles of gas in a box, and a bit of information is the knowledge of whether a given particle is on the left-hand side or the right-hand side of some divider, right? And here, this is my divider. So then you would read the left hand.
Why is it always a demon?
Sorry?
Why is it always a demon in these examples?
Why is it always a demon? Why not an angel? Well, angels don't cause your whole field to have a headache for 100 years, so I guess it should be a demon.
That makes sense.
So this division here corresponds to either going to the left or going to the right. And then we're going to further split the left-hand box into another half. And then, and then the one of them doesn't divide anymore. So that's kind of, let's call it 0, 0, right? That's here, here. So maybe I'll draw a line. And then the other one gets subdivided further in half, right? So maybe I'll do it the other way around. So this is 0, 1, 0. I guess if I read it, did you read it from right to left or left to right, Zhongtian? Like down the tree, like 0, 1, 0,
Left.
0, 1, 1,
Yeah.
like that.
Yes. Yes.
Okay.
Yeah.
Yes.
That was actually good.
Yeah.
And then I've got the one remaining one, which is doesn't. Yeah, I guess you're not using these, so I guess it's probably not that you subdivide the right-hand side at this node and that node. You just do it once, perhaps. So that would be like that. Well, okay. I don't actually know how to relate. You kind of want to relate the volumes of these pieces to these numbers that you're adding up. There should be proportions of the box, right? So I guess I need to divide the box in half at every step in order for that to work out, right?
So do you read these bottom up, not top to bottom?
Sorry?
Do you read these from the node up to the string, the empty string?
I'm reading them from the top down.
What did you?
I don't know if...
Did you write it? No.
Sorry?
It's the second. It's the third one, right? That should be like 0, 1, 1.
It's
Oh, yeah.
0, 1, 1.
Yeah.
0, 1, 1.
Okay.
I mean, we could do it either way, I guess, right? Okay, so...
Yeah.
So 1, 0, and then in half again. So this is 1, 0, 0. And 1, 0, 1. Yeah, I realize I'm reading it in the opposite direction you would usually read a string, but... Okay. Now, what are the volumes of those boxes? Well, if the overall, so if the volume of the square is 1, then this is 2 to the minus 2. This is 2 to the minus 3, 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 right?
Yeah.
And these, I mean, this 2, this is from LX1 is 2, right? That's this 2. And lx2 is 3. That's this 3. Tell me if I get any of the numbers wrong, Zhongtian. But
yeah, I think it's correct. Well, this should be 3 here, right?
Oh, I wrote 4. Yeah.
Yeah.
Yeah, so I thought I was writing 3. Okay. So then what we're doing when we sum up those r to the power minus li is we're adding up the volumes of the box. And the fact that it's less than or equal to 1 means we can fit them into the box. Right? So
Right.
this box decomposition it's kind of so canonical, it's back at the very roots of entropy and that whole story. So I'm sure that when they constructed this tree, this is what they were thinking of, or at least this is what someone grounded in the kind of people drew these boxes.
Like this box. Yeah, this way you can see like how they get that inequality.
Right.
I think.
Yeah. So I think that's where it
comes
comes from, but I don't know how to interpret the trick with the nth power in this picture, so that seems like it's actually a neat idea. But yeah, so the way to think about the Kraft-McMillan, the inequality, is somebody tells you, okay, I'm going to subdivide the box so many times, and I'll give you A of this size, and B of that size, and C of that size, and can you fit them into the box? And basically it says that the obvious constraint is the only one that matters. Like they have to add up to be less than or equal to 1, but which is clear, otherwise we wouldn't be able to fit them in. But there's always a way to fit them in. Something like that. All right, any further questions for the speaker? Seems not. Okay, thanks everyone. So next week, I believe Edmund is going to present the, I can never remember, is it asymptotic learning condition?
Asymptotic renormalizability something.
Yeah.
Renormalizability is asymptotic.
It's embarrassing because it's one of the few of Watanabe's papers that really has a distinct title from his usual pattern, but I still can't remember it. Yeah, so that should be interesting. So see you all next week, and thanks for joining us today.